And here we go, wonderful people. So we're going to start trig today. It's going to be short because we're missing like a bazillion people in class because they had to have their senior breakfast. I didn't have my senior breakfast. Oh, did I? I can't remember. So we're going to start trigonometry, a beautiful subject in itself. All right, so we're going to only have one section of the book. I'm not even sure how many pages to dedicate to this, but you can dedicate a whole textbook to this. So I guess we'll start with the easy stuff. And just a quick reminder. So trigonometry, usually we're going to be working with a right triangle. That's the base of this. Okay. Now, why is it so crooked? I'll make it better, I guess. Let me see if I can do a better job. So let me use the ruler. So that way, because you guys are perfectionists somehow. And
with your amazing computer, you should be able to do it.
I am. It is a good computer. Don't you feel like buying it?
No, when I had to write on it, it was really heavy.
Oh, because you gotta wake up in the morning and get your workout in.
I do my workout after dinner.
Really?
Yes.
What workout are you doing now?
I did chest.
You did chest?
Yes.
Okay, great. And what else?
I don't know. My mom constantly roasting me.
Oh, you go with your mom?
Yeah, I go with my mom, my dad, and like my brother. It's a good game.
Awesome. That's actually really cool.
It's not cool when they yell at you.
All right, so we have a triangle there. That's much better, right? And usually we call this angle theta, but you can call it whatever. That's a Greek letter, theta. And I don't know. What do you want to call the other one? It doesn't matter. Let's just look at theta, that angle.
Isn't it beta?
Well, we're going to call it beta. And we should call this first one alpha. Yes. A cos. All right. So let's just use this guy over here. And it looks like this. And you go like this. Ooh, that's bad. And you go like this. Oh my gosh, that's bad. It's like the pen is decalibrated or something like that. There. This is phi, and this is theta. These are Greek letters, and I guess they're capital, I think. So what you got to realize is that in a right triangle, the longest side is opposite the right angle. This is a right angle right here. And that's called your hypotenuse. I'm just going to put I don't know how to pronounce that. And then this side here, so with respect to theta, this side here is opposite. And with respect to theta, this side here we refer to as adjacent. I guess I can write it. But we just put ADJ for it. So I'm going to go ahead and erase those other letters. ADJ, adjacent. And so first we got to define our trigonomic ratios. So we say that the sine of theta equals opposite over hypotenuse. We say the cosine of theta is equal to adjacent over hypotenuse. And we say the tangent of theta is equal to opposite over adjacent last time I checked. Now, those are your basic, I guess, identities. We don't even call them. I say just call them trigonometric ratios. So now I'm going to go ahead and emphasize the same triangle, and let me go ahead and make another triangle here to the right of it. So wait, let me slide it perfectly there. So here we have another triangle. I could have just lassoed the other one, but whatever. This one is a little bit different than the other one, but it doesn't matter. So I'm going to go ahead and label this one. Here's our right angle. This is always the hypotenuse. It's opposite the right angle. And we're going to go ahead and call this theta. And this one, not a good theta. I don't know why I'm not. And this is phi. Now, with respect to phi, this would be opposite. This would be adjacent. You see that? With respect to phi. And I guess it's instructive for me just to attach some letters here. So this is where A, and this where B, and this where C. Then opposite here is BC. Hypotenuse is AC. And for adjacent, it'd be AB, AC. And this other one would be a BC, AB. So sine of phi is still going to be opposite over hypotenuse. But now I'm going to use these letters here. Right? And just now you're going to notice that this is AB all over AC. So notice how the sine of phi is equal to the cosine of theta. And then now when I do the cosine of phi, well, the cosine of phi is going to be adjacent over hypotenuse, which is BC over AC. And then we have the tangent of phi, which is going to be opposite over adjacent, which is AB all over BC. So notice that sine of theta is equal to the cosine of phi. And notice that tangent of phi and tangent of theta are just reciprocals of each other. Okay, well, that's all fine and dandy. But we have to make this more difficult, of course. You guys remember so, ka, toa. Wait, and I'm missing an H there. So, yeah, soka toa. But we had to spell it like this. Soka toa. And what that stands for is, well, the S stands for sine. This stands for cosine. And I'll move the board. This stands for tangent. And then this is opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Got it? Good? We know this, I hope.
No.
We don't know this?
No, this is because
Oh, so you don't remember it?
no, this was the last lesson I left.
Okay, so good. So it's gonna be refreshing, isn't it?
No, I hate trees.
Trigonometry is beautiful. Yes. Yes. No.
I hate unit circles more.
Well, let's talk about the unit circle, which is the next thing we're gonna do.
No!
So let's think about the unit circle.
That's not
Look, this is a circle. It has a center. It has a radius
Oh my god, no. I know.
of 1. The radius equals to 1. You see that? Now, I'm going to draw a line downward here that's perpendicular to this other radius. By the way, just to throw it out there, this is 1 as well. Now, we have an angle that's formed here. It's called theta. Now, right here, if this is a unit circle I'm going to go ahead and put a Cartesian plane on it. Bless you. So I guess the circle is superimposing a Cartesian plane. Could you please tell me the coordinates of that right there?
What?
What's the coordinates of that dot right there?
Where's that?
I'll make it in red.
The middle one?
That red one. What would that be?
One of the coordinates?
Yep. This is your X and this is your Y. What would be your X?
0.
Be careful. We go this way. How much units is it from?
Oh, 10?
1.
1?
And what's the Y?
0.
Yay. How about this guy here? What would that be?
0, 1.
Yes. How about this guy over here?
Negative 1, 0.
Yes. How about this guy here?
0, 0.
Good. We got. And who's this guy here? What's this guy in the middle there? And that's called our origin. It's the center of our circle. So far, so good, right? Now, what I want you to realize is that, like, I could have made this line here, and I could have made a different triangle. But the hypotenuse would always be, how long would that hypotenuse be? How long would this line here be? 1. It is always 1, no matter what you do. No matter where you turn that line, that hypotenuse is always going to be 1. And what's great about this is in the unit circle, see, as we go around a circle, our X and Y will change depending on which we're working with, which triangle we're working with, correct? Don't you agree? As we go around, the X and Y changes, but that hypotenuse always stays the same. So with respect, so this here, from here to here, we just say it's X. And here to here, we just say it's Y. So now let's apply the definitions we have on the left. We'll begin and say the sine of theta equals opposite over hypotenuse. Well, who's opposite theta here? Is X opposite or is Y opposite? So here, we're here. Here's theta. Who's opposite theta? This guy is opposite. So Y, and what's my hypotenuse? 1. So sine of theta really is Y. The Y coordinate is sine of theta. Whatever that Y coordinate is on that unit circle is your sine of theta. And so now when we do cosine of theta, 1 second. Yes. And Paul, resume recording. All right. So here we have cosine of theta. And what would be adjacent to cosine of theta? What would it be, X or would it be Y? Would it be X or would it be Y?
Be adjacent to what?
To theta. And then what's the hypotenuse? 1. So what's the cosine of theta going to equal to? X. Yeah, you see? Yeah. And so now we do the tangent of theta. So we have opposite over adjacent. So it's Y divided by X. Okay, super simple. So in a nutshell, that's the basics of what these ratios are. But of course, it's not going to be that way. You know, I'm looking at this here and there's so many little things here. I mean, I remember that this was a whole chapter of stuff that we had to go over. So what I want to do is I want to go ahead And before talking about how to graph these things, I want to go ahead and talk about some special triangles.
Good morning, gladiators. Is Christian Silva in the building? Please have him come to see Ms. Dagani. Christian Silva, please come to the main office to see Ms. Dagani. Thank you.
Okay, so let's do this. Okay, so here we have a triangle. And we have some special triangles, which we call the 40, one of this 45, 45, 90 triangles. And what you have to remember with a 45, 45, 90 triangle is that these two sides here are equal. So let's say if this were in a unit circle, this will be a 1. And guess what? This will be a 1. That's a possible thing. Well, you know what? Sorry. I should say this. This is 1 in the unit circle. Right? So these two are the same. So we'll just, this is going to be your X and your Y, right? And so do you guys have an idea how to solve this? Like, how can you figure out what X and Y have to be? Well, what do we use? Pythagorean? Theorem. What is it? A squared equals, yes, the hypotenuse. So what's X going to be? X squared plus Y squared must equal 1 squared, which is 1. But now notice, aren't X and Y the same thing? They're the same. So I can just say it's X squared plus X squared equals to 1. So that's 2X squared. You see what I did, right? Because X equals to Y. So I'm allowed to kind of like do that. And so we have this. And then I divide by 2. And X equals the square root of 1 over 2. And then we can go ahead and rationalize this. This is square root of 1 divided by square root of 2, which is just equals to 1 over the square root of 2. So let's go ahead and multiply both numerator and denominator by square root of 2. We end up with square root of 2 over square root of 4, and it's going to be square root of 2 over 2. And that means that this guy here.
Sorry for the interruptions, gladiators. Christopher Silva, if you're in the building, please come to the main office. Thank you.
And there we have it. We now have, because of this, we have that each of these sides are square root of 2 over 2. And so if I were to answer some basic questions, sine of 45 degrees is equal to square root of 2 over 2. Cosine of 45 degrees is square root of 2 over 2. And tangent of 45 degrees is going to be square root of 2 over 2 divided by square root of 2 over 2, which equals to 1. So this is a 45, 45, 90 triangle. And it's useful to know this. You can always just use your calculator to figure these things if you don't remember, but it's useful to know this. So now let's discuss a new type of triangle. I know you guys are writing. It's not a new type of triangle. It's a special triangle, special right triangle.
The 60/30.
Yep. And I remember in high school when I was taught this, I kind of just ignored it and didn't want to learn it for some reason because I felt like it was like gimmicky, like who cares? You have your calculator, just figure those out. But apparently these are special ones that they want you to know because they're kind of like special. I don't know. So let me go ahead and drag this to the right. So we have a 30, 60, 90 triangle. So we'll call this the 30, 60, 90 triangle. And well, I mean, what else can I say about this? If you take the sine of 30 degrees, the way I remember it is I say to myself, oh, the sine of 30 is half. And so I do this. Sine of 30 is half. And then if I want to figure out this one, I just go, okay, I want to figure out this one here. I say to myself, okay, well, x squared plus 1 squared equals 2 squared. So that's x squared plus 1 equals to 4. So x squared equals to 3. I think I messed up somewhere. Yeah, so then x equals to the square root of 3. And so now I know this is square root of 3. That's how I figure it out. But you don't need to do that. You could just remember it. But then if I want to express this as if it was a unit circle, I'll go ahead and lasso that for a second. I'm going to copy it and then I'm going to paste it. And then if I take 2 and I divide it by 2, this becomes 1. If I take 1 and divide it by 2, it's half. And I take 3 and divide it by 2 is square root of 3 divided by 2 is square root of 3 divided by 2. So when you do this, I mean, it doesn't matter which one you use. When you do the sine of 30 degrees, you get half. When you do the cosine of 30 degrees, you get square root of 3 over 2. And when you do the tangent of 30 degrees, you get 1 over square root of 3, which equals square root of 3 over square root of 9, which is square root of 3 over 3. Notice I rationalize this. So just in case you forgot. 1 over square root of 3 times square root of 3 times square root of 3, like that. We're multiplying by 1 effectively. We're multiplying by 1 effectively. Okay. So that's equals to square root of 3 divided by square root of 9, which is square root of 3 over 3. That's how we did that. That's how we ended up with this. Now, in the other triangle, I didn't worry about the other angle because 45, 45, 90, they're both the same angle. So the ratios are the same regardless of which angle you picked. But for this one, there is a difference. The cosine, the sine of 60 degrees, the sine of 60 degrees is now the square root of 3 over 2. The cosine of 60 degrees is half. And the tangent of 60 degrees equals, well, let's see. It's going to be the square root of 3 over 2 divided by half. So let's go ahead and work that out over here to see what it works out to be. The tangent of 60 degrees, I don't have to write that, I'll just work it out. Square root of 3 divided by 2 divided by half. Really comes out to square root of 3 divided by 2 times 2 over 1, which comes out to be the square root of 3. So this here, and that 1 is in the way, is just equal to the square root of 3 when you figure it all out. Okay. So far, so good. Not too bad. Just basic trig stuff. But now we have to start talking about graphing these guys. And what you got to realize with trigonometric functions is that they're periodic. They're periodic. That means they repeat their patterns. Okay, there's a pattern to them, and they just keep on.
Can I go back?
Oh, I'll go back. They keep on going and going and going and going. Yes. 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 But she's going to be missing my trig stuff. You know how important trigonometry is to living? I like your notes. All right, so now let's talk about graphing these trigonometric, whatever they're called, functions. Take care, Mama. Have a great weekend. All right, so what you got to realize in the unit circle, what's the biggest value in the unit circle? What's the biggest any value can get in a unit circle? Well, I know that that's the angle, but what about in terms of the coordinates? How big is the radius in the unit circle? No. How big is my radius? It's a very simple number.
Half the day.
Okay, in the unit circle, my radius is equal to?
1.
So what's the biggest value it can have?
1.
Yeah, it has its biggest values in coordinates when it reaches any of the extremes. Either at, so let's look right now at the unit circle I drew up here. Let's look at it for a second. I'll be done soon, guys. So here we have the unit circle. When we start here at 0 degrees, what did we say sine was? Sine is y. So what is the sine of 0 degrees? What's the value of y at 0 degrees? What's the y? 0. What's the cosine of 0 degrees? What's the cosine of 0 degrees? Cosine is going to be the x. What's the cosine of 0 degrees? 1. Don't be scared. 1. Now, by the time we got to 90 degrees, what is the sine of 90 degrees? Because sine is equal to y. How about the cosine of 90 degrees? It's 0. Because the cosine value is going to be the x coordinate in the unit circle. By the time we get to 180 degrees, what is now the y value of that coordinate? We're here now. It's going to be 0. For cosine of 180 degrees, it's going to be what? -1. For sine of 270 degrees, it's going to be -1. For cosine of 270 degrees, it equals to what? 0. And now, what about the sine of 360 degrees? Back to 0. And how about the cosine of 360 degrees? 1. By the way, when we rotate this way, counterclockwise, the degrees will be positive. If we rotate clockwise, downward, the degrees will be negative. Now, what I want you to understand is as you keep on going and spinning around in circles, the degrees keep on going and going, but the values keep on repeating. And this is what we mean by it being periodic. This is what we mean by it being periodic. Now, we did some special right triangles right now. And we said that the sine of 30 degrees was half. And we said the sine of 45 degrees was what? Square root of 2 over 2. All right. Now, just to let you know, the values for sine and cosine will always be between 0 and 1, inclusive. It's a ratio between 0 and 1. Tangent is different. Now, just to give you a decimal approximation of square root of 2 over 2, .707. It's actually an irrational number, but that's a good approximation. Why am I going through this trouble? Because right now, I plan to kind of quickly show you how to graph these and what indeed it means to be a periodic function. So if we were to graph sine, for example, and let's just say that f of theta equals to sine of theta. Let's just say that. And I drew this here. In this case, the highest value is 1. The lowest value is -1. Okay. And here we have our angle. Okay. We're using degrees, but you'll know later on we won't be using degrees anymore. We'll be using radians, which is, I think, better. But so, you know, we have 90 degrees, we have 180 degrees, we have 270 and 360. And if you look at the value for sine of 0 degrees, which will be here, it's 0. But at 90, it's 1. At 180 is 0. At 270 is -1. At 360 is 0. Now, just to throw this in there, see, midway here at 45 degrees, it's like 0.7. Midway here, it'd be like -0.7. And so all the midways are like there. Right? Something like that, 0.7. So let's just say 0.707, right? And then just because we can, 30 degrees will be somewhere there. It'd be halfway, like there, right? And we do it here, it'd be here. And if we did this, it will look like this. It'll go up. Then, oh man, me pasé. There, no, we're good. It go up. I put this -1 here. Should be at 90, it's 1. At 180, it's 0. So I drew it in the wrong spot. You see? And then it comes like this. And goes right back up. So these, I did wrong. That's how it's going to look. In other words, here it's there, here it's there, and there. Okay? That's how sine will look like. And guess what? If we continue this with more degrees, it keeps on doing the same thing. All right? And then we did this with tangent. Sorry, with cosine. It'd be similar. It'd be similar. It'd be a little bit different though. So that's why I say similar. So if we said f of theta equals cosine of theta, of course, the maximum value is 1. The minimum value is -1. And at 0, it's going to be 1. But at 90, it's going to be 0. And at 180, it's going to be -1. And at 270, it's going to be 0. And at 360, it's going to be up here. So this one, and if you go through the trouble and figure all this, it's going to look something like this. Super simple. And if you keep on extending it, it kind of feels like it's a shifted form of sine theta. So cosine and sine are just, they're shifted. You can imagine shifting sine by 90 degrees to the left, and it's going to be cosine. And that's important because we're going to develop certain trigonometric identities that we can use to solve trigonometric problems. So now let's go ahead and finish up with tangent, and I'll call it a day for today. You know, so we can do f of theta equals the tangent of theta. All right. And let's see if we can make it work. So here's what happens. Let me scroll for you guys. I wish that scrolled for me. I could make it scroll, but then I have to share a link. And it just takes extra time. So here we have tangent of theta. Tangent of theta is strange looking.
Good morning, gladiators. Benjamin Heath, please come to the main office. Benjamin Heath, please come to the main office. Thank you.
We haven't really talked about sine of theta, but we should, because when we come back here, remember I told you that in a unit circle, and I'm not sure I talked about tangent, but I should have. That means I'm either going too fast or not being thorough enough. See, tangent of theta in the unit circle. So this is 1 and this is theta. This is y and this is x. That's what you have to remember. It looks like that. Tangent of theta is just y over x. But what's y? Well, if we remember y, sine of theta, and you can't see that because I rolled too high. If we remember, sine of theta is equal to y, and cosine of theta is equal to x. So tangent of theta really is sine of theta divided by cosine of theta. Why is that important? Why is that important? Well, what happens is at tangent of 0 degrees, really is sine of 0 degrees divided by cosine of 0 degrees. Well, what's sine of 0 degrees? We said sine of 0 degrees is the value of y at that, and it's going to be 0. divided by 1. So sine of 0 degrees is right here. But by the time we get to tangent of 90 degrees, we have sine of 90 degrees divided by cosine of 90 degrees. Well, guess what? That's 1 divided by 0. That's not possible. We're not allowed to divide by 0. So what that does is create something called a vertical asymptote. So what we do is we say, oh, what about tangent of 45 degrees? Well, the tangent of 45 degrees is sine of 45 degrees divided by cosine of 45 degrees, which is going to be well, what's sine of 45 degrees? Square root of 2 over 2 divided by square root of 2 over 2. What does that equal? What does square root of 2 over 2 divided by itself equal to? 1. There it is. So this is 1. And we did negative 45 degrees on the other side. It's going to come out to negative 1. And at negative 90 degrees, there's another asymptote. In fact, this will look something like, if you went out, it looked like something like this. And guess what? Every 180 degrees, the asymptote is repeated. And you're going to notice that this here, halfway there and halfway there, repeats itself, and it looks something like this. It's different. Okay? Only if you're careful. Now, just to emphasize this notion of periodicity, the period for sine is basically, it repeats itself every 360 degrees. So it has a 360 degree period. The same thing happens with cosine. But with tangent, the period is 180. With tangent, the period is 180 degrees. The great thing is that it gets more complex, and the period can be changed by altering maybe the angle that it has. So that's it for today, wonderful people. I'm going to put this up there if you want to take a look at this. I haven't done any problems from here, but I will eventually do so. So give me 1 second. Now my wife is calling me. Incredible. And stop.